business, let's take a look at results. Okay, so this is the final round for the practice round, 3 rounds. Here's the final standings over here in the right-hand column. So congratulations to the Racketeers. They were consistently high the whole time. Second place, Rack and Roll, who made steady progress through the field. Won't Rack down is next. Look Rack at it. Look Rack at it was down and up and down. A lot of teams kind of stayed where they were. Thunder Muffins kind of dropped significantly throughout. But at any rate, this is the standings for the practice round. Okay, so this was the sales versus price plot for the 3rd round. And it's kind of interesting because one team, who shall remain nameless, Spice Racks, set their price at 0 in many cities. And in fact, garnered a large sales volume by giving it away free. But it did not, at the same time, it did not steal demand from all the other teams who set more normal prices. And in fact, if we look at the next page, these are the sales versus price over the 3 periods, with the blue circles being the last period. So we see that even if you exclude the 0-priced Spice Rack, the other teams actually have more demand rather than less. So that was kind of interesting. So nice try, but doesn't seem to have worked too well. Okay, these are just your net assets by period. So the Racketeers just made steady progress. So did Rack and Roll. You should be able to make money in this game. So for teams that didn't make money, 30 Rack LLC, that's really not very good. Here's the stock prices. The top teams also had the top stock prices, although won't Rack down. Seemed to jump up right at the end to have the 2nd highest stock price. So the stock price starts at 20. The Racketeers ended about 23. So they made something like a 15% gain in 3 periods, or 5% a period, which is pretty good. Gives you some idea of what can be made in the stock market if you do well. On the other hand, most of the teams were fairly close to the initial $20 stock price. Here are the sales figures. So Spice Rack, who set their price at 0, sold 36,000 units. But beyond that, Racketeers and Dunder Muffins both sold close to 20,000 units. So kind of interesting numbers there. What do we see here? Equity holdings, like, Racketeers equity holdings were almost double that of Rack Attack. 30 Rack had no cash whatsoever at the end. They had a ton of raw material, $100,000 worth of raw material at the end. I suppose you could consider investing in raw material as something you could do. I can't remember how it's evaluated in the net assets. I think it's at its full value, but that was certainly in the presentation on the first week. Current stock prices, earnings per share. Again, 30 Rack was negative. I'm not sure, I guess look back at it, apparently announced that they would sell all of their own stock. Of course, it won't take place because there's a 1-period delay and the game is over. I'm not sure why they were thinking of doing that. I can't imagine it would have, where was their stock price? I'm curious what effect it had on their stock price. So let's look back at it. It looks like the fact that their stock was about to be sold off may have had a negative impact on it. I'm not sure if that's true or not. Now, one last thing. These are, at the end of the game, the short sales that have occurred, okay? In particular, what this means is that this is team, oops, sorry about that. Team K here, there were 3 teams, teams G, I, and L, who short sold team K. In fact, short sold 5,000 and 10,000 shares. That's not, these are not dollar values, these are share numbers. They short sold team K that much. Now I have to go back and look and see if that was all legal as far as your margins. I haven't had a chance to do that yet. But also, if I was team K, I might be a little suspicious. Could there be some collusion between teams G, I, and L in trying to drive down their stock price? It's an interesting question. I would have thought team K would have complained to the Securities and Exchange Commission. In this case, there's not enough time to investigate, but you should keep an eye on, and you can keep an eye on what other teams are doing with your stock. And if you see something suspicious, at least think about what's going on there. All right, anybody have any questions? No? Who's the head of the Securities and Exchange Commission? How much power does he have? The answer is ultimate power. So don't screw around in the real game or you will get dinged. Okay, I'm not seeing any questions. Let me go back here. Oh, chat. Okay, no problem, Dylan. Okay, so we start the real game. This time we're going to play 12 periods. And you may recall that posted way back at the top somewhere is the, where is it? The team name and city bid turn-in sheets. All right, so can you guys see these? Sachil, can you see it? Yeah. Okay, so you got to fill these out again. Your team number has not changed. Whatever team number you were, you're getting that's still your team number. You can keep the same name or pick a new name if you want. You can pick a new password if you want. And you can bid on your first plant location. And we'll decide which teams get which cities in the same way we did in the practice round. So this sheet is posted, and we would like for you to fill out the sheet and email it to Sachil by 5 o'clock today. once she has them, sometime in the near future, after that, she will reset the game. And we can get started. Now, one thing I want to point out, which hopefully you already know, but so here's like the industry report screen, and you can download the data, right, from the industry report into a spreadsheet, right? So if you just go to the industry report and click this period, just click download without selecting a period, just click download. It will give you the latest period worth of data. So you can go back to the previous period, the previous period, download that data. So, I mean, that is always available. However, once Suchil starts the game over again for the real round, all that data will be gone. So if you're interested in maintaining any of that data, download it, you know, before 5 o'clock, 6 o'clock tonight.
Professor Storer?
Yeah.
When you download that data, the spreadsheet that it gives you is empty. Like none of the values are populated.
That's not true. I just did it. I mean, that's how I get the data to make the presentations that I make every week. Works fine.
We can check it again if you have a problem, Alexander.
Yeah, I was also having a problem, but only with the company reports. I couldn't download older periods of that.
I usually don't try that. Obviously, you could only, you wouldn't be able to allow to download any reports except your own. This one I have not tried. Suchil, have you tried this?
I had no problem, but we can check it together to see.
Okay, any other questions? Okay, so this is the real round. So next, we go on to our weekly lecture. All right. So what we're really talking about mostly today are transportation problems, but it's within the realm of supply chain management. So you may recall at the beginning of the semester, I said that because you take this class, you don't have to take supply chain management 183 or whatever the number is, which is normally one of the required business classes for business students. You don't have to take it because of this. So I kind of feel obligated to talk a little bit about supply chain management. It's kind of a buzzword for what we used to call logistics. So the idea is that you talk about supply chains, which tie together multiple suppliers, facilities, plants, distribution centers, customers, kind of all together into a system. And it deals with problems like production scheduling and inventory and transportation and distribution. And it kind of looks at the system as a whole. And in some sense, that's interesting because when I was your age, computers were in their infancy. Basically, each facility kind of managed itself as a single unit and didn't see itself as part of a larger system because it was too complicated to do that. So everything got done by a guy a person at plant A calling somebody else at warehouse B and just doing everything over the phone and on paper and things like that. Now we look at it more as a system where you may have suppliers, you may have people who build sub-assemblies that then go to a final assembly plant. that then they're sent out to distribution centers and finally sent out to customers. And like, this is what a supply chain might look like. And that's the supply chain for a single product. And in each of these nodes in this network, you may have multiple products flowing through there through a whole bigger system, right? So now that we have sort of computational abilities and system engineering abilities, we can look at these systems kind of as a whole rather than the individual component parts. And so that the study of that, this thing as a system, is basically what supply chain management is. And there's all kinds of supply chain or logistics problems. Sourcing, right? So where should I get my supply from, right? So in the game, it's where should I get my raw materials from? I mean, that's not a decision in the game, but if you think about the game, that would be it. Should I try and go with a sole supplier? Should I buy all my raw materials from one supplier, or should I have multiple sources for my supply? And this is actually an argument that has gone back and forth. 15 years ago or so, there was a big move for single source suppliers, where the goal was to have one source as a supplier, and then to work closely with them to make sure everything went really well. That suffers from a key problem, which is if that single supplier has a problem, like if they get hit by a hurricane or something, now you have a big problem, right? So people more recently have been studying things like supply chain disruptions and how to be able to endure supply chain disruptions. How should I distribute my stuff, right? So which customers should I serve from which locations? So a good example of that is Air Products and Chemicals. They're a local Fortune 200 company that supplies liquid nitrogen and liquid oxygen, and they have something like 100 plants that produce liquid nitrogen, liquid oxygen around the country, and in fact around the world. And every day, and they also have customers, right? They have customers all over the country, whether it be hospitals or whether it be food manufacturing plants or several other kinds of industries. And each customer has a certain demand on each day. And you have to decide from which plant you will supply each of your customers. It's kind of an interesting problem. Air Products has basically two costs that they have to deal with. The cost of trucking their liquid nitrogen and oxygen to the customers, and the cost of electricity that they use to distill, to take air and distill it down into liquid nitrogen, liquid oxygen. Production, right? So how much should I produce of each product in each period? So that's kind of production scheduling. Then there's inventory. Do I want to keep inventory of finished goods? Do I want to keep inventory of raw materials or supplies? How much? And then finally, transportation. How do I ship the stuff? It's more like this Air Products problem. How do I ship stuff to my customers in the cheapest way? All right, so the first problem we're going to consider is something called the transportation problem. It's a well-known optimization problem. And it's basically, it goes like this. You have customers with known demands and locations. You have plants with known supplies and locations. We know how much it costs to transport between each of these entities. How do we decide where to supply each customer from? So you can think of a graph that looks like this. So over here we have plants in 3 cities, and we have the supply. So this is how much, these could be plants or warehouses, I suppose. Well, let's call them plants for the time being. And this is how many units we have available at each plant to fill the demand. Over here, we have all of our customers and their demands. And then on each arc, we have the cost of shipping. So It could be zero, right? If we supply Chicago from Chicago, maybe the cost is zero. The point is that on each arc, we have a cost. And presumably this cost is dependent mainly on the distance from the plant to the city. Okay, so CIJ is basically the cost of shipping 1 unit from plant I to city J. XIJ is our decision variable. It's how many units we ship from plant I to city J. Basically, in our game, the cost would look something like this, right? That's ignoring that $200 per truck cost. But okay. And then the two constraints in this model are we cannot ship out of plant I. So if we sum over all of the customers, XIJ, that's how much we're shipping from I to all of the customers J. We can't ship more than we have, right? The amount we ship out from I has to be less than the supply. And then the amount that we ship in to each customer has to be greater than or equal to demand. You could argue that this should be equal to. It doesn't really matter because you're never going to ship more than you need to. Otherwise, it would cost you more money, and we are minimizing. And then we have, of course, you can't ship a negative amount. That's our final constraint. So in the examples that are posted, this is the solver version of the problem. It's pretty easy. We start with our distance matrix like we often do. These are our decision variables, how much to ship from the plants to the cities. I really don't need all of these rows. Probably I only need the rows where I have plants, which are Chicago, where I have 2,000 units, LA, where I have 4, 4, 6, 7 units, Boston, where I have 3,000 units. So these are my supplies at my 3 plants. Here's the demand in each of the cities. My constraints are going to be that the amount received, ultimately, if I add up this column, that's the amount shipped into Chicago. That is going to be summed up here, and this has to be equal to the demand. Come over here. If I sum up over a row, that's how much I shipped out of Chicago. That will be summed up here. The amount shipped has to be less than or equal to the supply. So those are the two constraints, basically, the green and the pink. And then my total cost is just going to be the distance matrix times the amount shipped matrix times $0.005 per unit per mile. Okay, so that is pretty straightforward. Our solver model simply has this cost cell we want to minimize. The yellow decision variables, those are these guys here. Those are the yellow matrix decision variables. And then the two constraints I mentioned. All right, this is a linear problem. And so we use simplex LP, and it solves pretty easily. In fact, it tells us how much to ship from each city to each city. So we supply Chicago from Chicago. We supply Seattle and Los Angeles and Denver from our plant in LA. We supply Boston and Washington from our plant in Boston. And we supply Miami from both Chicago and Boston. And the reason for that is that we used all of our goods in Chicago. If we had had more supply in Chicago, we would have used it for Miami, but we ran out, so we had to supplement it with supply from Boston. Okay, so that's a pretty straightforward model. Okay. And next we have a better version that can solve that problem and more. It's called the transshipment problem. Okay. So imagine now we have nodes in the network which represent our cities, and we have arcs that we can ship through. So we can ship goods through a whole path of nodes, right? So we could go along that red path, we could go along that blue path. And why might that be something we want to do in the game? The answer is if we have warehouses, right? So we might send units from our plant in LA to our warehouse in Chicago, and then from our warehouse in Chicago to our customer in Washington. It wouldn't be a direct shipment, right? So it's sending goods across a network. And in particular, this is how it might look in the game. We have plants in LA and Boston. We have a warehouse in Chicago. And in order to supply, let's say, Dallas, we might do that by sending stuff from LA to Chicago and then Chicago to Dallas, or from Boston to Chicago, Chicago to Dallas. The reason we want to do that is because these plant to warehouse arcs, these red arcs, have a lower price, right? That's the rail rate rather than the truck rate represented by the darker black arcs. Okay. So in this particular model, the decisions are how many units go across each arc in the network, right? So every arc in the network has a cost, whether it be the rail rate or the truck rate. And we, for every unit we ship along an arc, we incur that cost. We want to minimize the cost subject to constraints. And it turns out that the constraints in this problem are particularly easy to state. Basically, it's for every node, the flow in plus the supply in that node is equal to the flow out plus the demand, right? So you can think of if you have demand at a node, that's like taking units out of the network or out of that node, right? So the total flow out is the flow that you ship out from a node plus the demand you take out of a node. So that's the total outflow. And if you think of a node having supply like a plant node, that's like injecting units into that node, plus you might ship stuff to that node as well. And so the only constraints in this model are that basically the flow in equals the flow out. And that, of course, has to be positive. All right, so this is the formulation. It's pretty close to previous one. Our costs are computed basically the same. Per unit cost times the flow across each arc. These are the flow in equals flow out constraints. And then we have that they have to be positive. Ignore these guys down here. These are extraneous constraints that might be useful to make solver work better, but solver works well enough now without these. So that would be our next example in the examples. And by the way, I should mention that this is one example of a particular type of optimization problems. These are called network flow optimization problems. And they appear in things besides transportation. They appear in all kinds of other situations as well. Okay, so it starts fairly similar. We have our distance matrix. And this, now we have the amount we're shipping from each city to each other city. Okay. And we have our cost matrix. So now this is what's interesting, because in this example, the arcs have different costs because of the warehouses, right? So we can ship from LA and Boston to Chicago at a much lower price at the rail rate than any of the other arcs. So the other arcs have it as 0.01. So I figured it's 0.005 plus I added in another to account for the truck costs as an approximation, right? But again, the point here is the costs are different, right? So in the end, my shipping cost is going to be computed by doing a sum product of the distance matrix times the amount shipped matrix times the cost matrix, right? So it's a triple sum product, and that will give us our total cost, all right? So then we have our supply. In this example, we have a supply at our plant in LA and a supply at our plant in Boston. Our warehouse has nothing to start with. So these are our supplies. We have our demands here, okay? If I sum over this row, that's the number of units that are shipped into Chicago. So that's this sum here. So I take the demand plus the ship, that's the total sum out for Chicago and all of the other cities. On the other hand, we have supply here and here. And if we sum over the row, that's how much is shipped into or received by that city. If I add these two together, I get the sum in to every node. And so the constraint is that this row has to equal this column, right? Sum in equals sum out. All right, and that's all you have to do. So the solver model is particularly simple. Basically, one set of constraints, and it's linear and it solves very easily. But it's a little bit different to interpret. So I wanted to sort of go through the interpretation here, right? So if we look at our warehouse, okay, in Chicago. So Chicago had a demand of 996. We shipped 1,453 units in. What am I doing here? So basically, at one point, we had 2,422 units. We kept 969 for our customer in Chicago. We then shipped 643 to Miami and 805 to Dallas, right? Similarly, in LA, we had an initial supply of 4,467. We kept some of them for our customer in LA, and then we sent 878 to Seattle customer, 849 to our Denver customer, and we sent 2,081 to our Chicago warehouse, right? So you can piece it back together what actually happened or what the decisions were by going through an exercise like that. Okay, so we could add in other enhancements to make it more realistic. You could put in the fixed cost for trucks. That could cause solver problems because it now becomes nonlinear. We could add in plant and warehouse location decisions as well as our transportation decisions, and we're going to do that next. And then we could attempt to deal with the fact that demand is not actually known, but rather is a random variable. So we'll talk a little bit about that as well. But first I want to go to the next example, because it is a bit more complex, but it's actually starting to get close to being something that's useful. All right, so in this model, we are going to decide where to open plants. We're going to decide how many units to ship from, well, actually, I'm getting ahead of myself. We're going to decide how many plants to open. We're going to decide how many production lines to build in each plant. We're going to sort of decide how many warehouses to open. and we're going to decide how much to ship across our network, right? We make all of those decisions in one model. So kind of throwing everything together. So basically our constraints are that the open plants decision variables have to be binary, right? 0 or 1. Our lines built, the number of lines we build have to be an integer number of lines. Okay, the lines built has to be less than or equal to 5 times the plant open decision, right? So if you don't open the plant, you can't build any lines, right? If you do open a plant, you can build up to 5 lines, right? So can't build lines if you don't open the plant. And then the other constraint is just our network constraints, that the sum in equals the sum out. So these represent the sum in and sum out columns over here, or sometimes the network flow decisions. Now, how do we do the costs and the warehouses? All right. So if you were to open this one here, this means we open a warehouse in Miami. So we get the cheap costs, right? So the way I implemented that was basically the cost to ship to a city depends on if there's a warehouse open or not, right? So I did a 1 minus warehouse times 0.005 plus warehouse open times 0.005. So that would be the cost, right? It's either 3 zeros or 2 zeros, depending on these decision variables. Then it would be times the units shipped times the distance. So these units shipped, that's a decision variable. And this warehouse open is another decision variable. So now we have one decision variable multiplied by another decision variable, which makes this a nonlinear model. And in fact, if you make these warehouse open as decision variables in the model, Solver will crash and burn. That's too hard of a problem for Solver to solve, right? So I decided the best I could do was to make this sort of a manual decision, right? So what you could do is you could say, okay, I'm not going to open any warehouses. So I make those zeros. I don't open any warehouses. And then I can run the model. And in this case, there's an assumed demand here, which I forgot to mention, right? But we're always going to make some kind of assumption about what the demand is. And it's somewhere here in this model. Where is it? Yeah, so here's the assumed demand for this particular model. So I ran the model with no warehouses, and it told me I should build plants in Miami, Seattle, Denver, and Washington. And then my cost was about 737 million. And I said, what happens if I put one warehouse in Seattle and run my model? Well, then it tells me to build plants in Miami, Denver, and Washington, and my cost is $669,000. I can keep playing around with this, right? So I got it down by opening warehouses in Miami and Seattle. It then decided I should have plants in LA, Dallas, and Washington, and my cost was now 637 million. And, I could play with this some more. I kind of like the idea of having warehouses in faraway places. I'm gonna put one in Miami. I'll put one in Seattle. I'm gonna put one in LA. And I'm gonna put one in Washington, just for grins, right? Okay. So now, let's solve the model. This will work pretty quick. All right, so look, I got my cost down below 600,000. Right, so that's an even better solution. I got plants in Boston, Denver, and Dallas. Right? So this is a pretty cool model. This is something you could actually use in the game. Of course, you'd have to adapt it to 12 cities instead of 8. Fair enough. Okay, so the other thing we talked about was stochastic optimization. So the big problem with the models I've been showing you is you have to assume what demand is going to be. No, that's not too bad. I mean, you can control your demand to some extent by setting your prices, right? So you can kind of, say, here's the demand I'd like. How should I set my system up? However, there are ways that you can take randomness into account in these optimization problems. So I'm going to start with the simplest of all stochastic optimization problems. It's called the news vendor problem. So imagine that each day a news vendor has to first buy newspapers from the newspaper company, which he or she then sells on the street for 75 cents a piece. If the news vendor is not able to sell all the papers by the end of the day, any leftover papers can be brought back to recycling, for which the news vendor gets 10 cents a piece. So the problem here is that demand is random. We're going to assume we know the distribution. And so the decision is, how many newspapers should we buy at the beginning of the day to maximize our profit? All right, so this is a classic business problem. So one of the issues you have to deal with in business is that demand is random and it's unknown, right? And so demand is random, demand is unknown. You have to decide how many units to produce in the face of random demand. How do you make that decision? So the news vendor problem captures that fundamental business decision in a very simply stated problem. Okay, so how many papers to buy? Demand is a random variable. So what's our sales revenue? Our sales revenue is 75 cents for every paper that is bought. So how many papers will be bought? Well, whichever is smaller, the demand or the number of papers you buy. If you buy 20 papers, but demand is only 18, you can only sell 18. If you buy 20 papers, demand is 30, you can still only sell 20 because you can't sell more than you bought at the beginning of the day. So that's the sales revenue. Your cost is simply 35 cents times the number of papers you bought. Then your salvage revenue is 10 cents if there are any left over. Right? So if the number bought is greater than the demand, there will be that many papers left over. Otherwise, it's zero. And then your total profit is sales revenue plus salvage revenue minus cost. So this is a simple, solver model. First is you start with your demand scenarios, right? So each of these represents a demand scenario. I've sorted them, but I generated these randomly. In fact, I generated them from a normal distribution with a mean of 150 and a standard deviation of 10. All right, so these represent my random demand scenarios, right?
Professor Stir, we cannot see our screen at the moment.
Thank you. Glad you're here, Sachil. Okay. Start over again. So column F here, these are my demand scenarios. They were generated randomly, right? So they represent different demands that might happen. If I know the distribution, I can generate them from that known distribution, right? So the idea is that for each, and so here's my decision. How many papers do I buy, right? So I can compute the revenue, the cost, and the salvage revenue, and then those go together to make the profit. So if I buy 100 papers, turns out the demand is always greater than 100, so I always sell all of them. I make that much revenue, right? But if I buy 150 papers, right? So now I don't necessarily sell all of them. Sometimes I have some left over, and my profit changes. So what I want to do is I want to maximize my expected profit. So for expected profit, I'm just taking the average of the profits over my scenarios, right? And if you were to ask me, why do I have 30 scenarios? The answer is, I don't know. If you don't think that's enough, create more scenarios. And you get a more accurate answer. So here's my average profit. That's just copied from this cell down here. And so my optimization model, this is my single decision variable. This is my objective function. And in fact, there are no constraints whatsoever. So it's a very easy solver model. Maximize my profit by changing the number of papers I buy. It is a nonlinear model, so I have to use GRG nonlinear. It's nonlinear because of the mins and max functions that are in there. And it tells me that the answer is 159 papers. Okay, so this is a way that you can deal with random variables that exist in your models. For example, demand. Now, can you? You probably can't see that, can you? Never mind. Okay, so there's a whole area in optimization called stochastic optimization or stochastic programming. And basically it involves creating these scenarios that represent the randomness in your model. I'm going to skip over this stuff here because I don't want to talk about it. And I'll talk a little bit about this kind of one of the most common kinds of stochastic programming is called two-stage stochastic programming with recourse, I'm sorry. So it's like a two-stage problem where there's two sets of decision variables. One set of decision variables X you make before the random variable outcomes are known. Then the second set of decisions you make after the random variables are known. And so the goal is to minimize the sum of the stage 1 costs plus the expected stage 2 costs. Forget the formulation, but an example, like one example in the game is stage 1, you have to decide how many units to ship from your plants to your warehouses before demand is known. And then after demand is known, after demand is realized, then you have to decide how much to ship to the customers from the plants and warehouses. So you could have various demand scenarios and try and solve that problem that way. I don't want to get into the details of this too much. Right, this is not the problem that you have. Basically, what you have to do is you have to decide a demand order and the supply order. All right. I think I'm going to stop there. I don't want to go anymore because I think that okay, so I have 5 problems. I actually like most of these problems this time. Okay, so it's probably not unrealistic in the game to have a model of the relationship between price and demand. As some kind of a linear model looks something like this. It might vary from one city to the next. So basically that's what I'm saying, is in each city I've built a demand price relationship, which is linear, given these coefficients, A times price plus B. And so the problem is, given these parameters, determine the price to set in each city, assuming you have a fixed supply of 8,000 units. Okay, so the next one continues the first one. So we're going to add on to it. We're going to bring transportation into the problem, right? And transportation and manufacturing costs. So this was just maximizing revenue, but we also have to worry about costs. So the costs we're going to consider are transportation costs, manufacturing cost, and raw material costs. We're going to ignore overhead because overhead is going to be the same either way. So we can honestly ignore it. Okay. So we're going to decide the price to set in each city, how many units to supply from each plant, subject to the normal transportation constraints. You can't exceed supply, and you must meet demand. Okay, the third problem is basically a transshipment problem. We're going to do 12 cities. Again, all of these should use all 12 cities. Yeah, so this is basically a transshipment problem. Next one is revenue management. So I'm sure you've gone to the airport, you're about to get on your plane, and the announcement comes, we've overbooked this flight. Is anybody willing to take $500 to take a later flight? So the overbooked flight. So this is a decision on how many tickets should an airline sell for a particular flight. Given that the demand or that, the number of passengers that actually show up or don't show up for the flight is a random variable. So we have 100 scenarios which represent the number of people that don't show up for the flight, and you get to solve for how many tickets to sell, given some information in the model. And then the last one is actually posted in a spreadsheet. Okay, and this is basically what you have to decide in the game. All right, so here's the problem. Assume that you have plants in Los Angeles and Washington and a warehouse in Nashville. Okay, the demand order says which city you supply first, which city you supply second, etc. Right? So whichever city you give a 1, that means that we're going to supply the customers in city 1 first. And then if I put a 2 here, that means we're going to supply customers in Boston second, etc. Now the problem is you might run out of supply at your plants or your warehouses, right? And so they may end up being supplied from somewhere else. So you get to say where you want this to be supplied from. So for Chicago, I'm guessing you'd say I'm probably, given my choice, I'd supply from Nashville first, Washington second, LA third, simply because of the distance. Right? So that would be your sort of from preference. But like I say, if this was number 12 here in the order, then I may well have run out of units from in my warehouse, and I may even have run out of units in my plant in Washington. I may end up having to serve it from my plant in LA. That's going to be expensive. Okay? So typically this part of the problem is pretty easy. I'll even tell you, you should supply from the closest place if you can, right? So here you're just going to pick this order based on what's closer to each of these cities. The question over here is, how should you decide this demand order? Which cities should you fulfill the demand for first? Which one second? Which one third? Okay, so that is the problem I would like you to address there. Okay, so this is Some of these problems are different than past problems, and I'll tell you that to start with. And so they should be challenging. To summarize, don't forget to give your team name and city bid sheets in the next couple of hours. Email them to Sachil. If you want to stick around and work on either the game or the homework, Sachil and I will be hanging out, and Sachil will put you into breakout rooms for your teams. Before we do that, one last time, does anyone have any questions? Okay, Sachil, send them away.